Welcome to part 1 of this video playlist about the preparation of nitriles by alkylation of cyanide. The playlist consists of 4 videos, this first one being about alkylations with alkyl halides and sulfonates. At the end I've also included examples of alkylations with weaker electrophiles, such as esters and alcohols. Part 2 covers alkylations of cyanide with epoxides, and in part 3 we'll have a look at the cyanation of alkenes. The last video is about the preparation of cyanohydrins by alkylation of cyanide with aldehydes and ketones. A number of nitriles are important industrial intermediates and are being prepared on a huge scale. One of them is acrylonitrile, which is prepared mainly by gas phase amoxidation of propene. Alcohols and aldehydes can also be converted into nitriles this way. The main uses of acrylonitrile include the electrochemical dimerization to adiponitrile and the preparation of succinonitrile by Michael addition of hydrogen cyanide. Both dinitriles can be hydrogenated to diamines or hydrolyzed to the dicarboxylic acids, which are important building blocks for polymers. Adiponitrile can also be prepared by direct nickel-catalyzed hydrocyanation of butadiene. A further important product is nitrile rubber, suitable for the production of disposable rubber gloves and many other products. This chemically resistant synthetic rubber is prepared from acrylonitrile and butadiene. Hydrogen cyanide is prepared on a large scale by amoxidation of methane. In liquid form, it is stable in the presence of acids, but can polymerize violently if bases are added. Polymerizations do, however, require a certain concentration of monomer, and dilute solutions of hydrogen cyanide do not polymerize as readily as the neat compound. Hydrogen cyanide is a weak acid only, and alkali cyanides are therefore strong bases. This basicity can cause elimination and other unwanted side reactions during alkylations of cyanide, as I will show you later. Sodium cyanide can be prepared from hydrogen cyanide and sodium hydroxide or from sodium cyanamide. The latter is an older strategy from the pre-oil era. One further important intermediate is cyanogen chloride, which is obtained by electrophilic chlorination of hydrogen cyanide. This compound is lipophilic, volatile, and sufficiently stable toward hydrolysis to enable its preparation in water. Thermal trimerization of cyanogen chloride yields cyanuric chloride, a critical intermediate for the manufacture of triazine herbicides and sunscreens. Other uses of cyanogen chloride include the preparation of cyanates from phenols as monomers for polymeric triazines. These polymers show valuable mechanical, dielectric, and other properties. Reaction of cyanogen chloride with sulfur trioxide yields chlorosulfonyl isocyanate, another useful intermediate for various applications. And at high temperature, cyanogen chloride undergoes homolytic carbon-chlorine bond cleavage. The resulting chlorine radical can initiate a radical chain cyanation, for instance of acetonitrile or cyclohexane. These are inexpensive approaches for the manufacture of malononitrile or cyclohexane nitrile, but require some optimization and specialized equipment. Alkali cyanides have 2 problematic properties: their high basicity and low solubility in organic solvents. Because of its small size, cyanide is also strongly solvated in protic solvents, what decreases its nucleophilicity and increases its tendency to act as a base, like fluoride or hydride. These problems can be avoided by using trimethylsilyl cyanide or cyanodiethylaluminum in aprotic solvents as synthetic equivalents of cyanide. Unfortunately, both reagents are way more expensive than alkali cyanides, but many organic electrophiles will not react with the latter at all. Further alternatives are the cyanohydrine of acetone or neat hydrogen cyanide, but these are more difficult to handle safely than the silicon or aluminum derivatives. Trimethylsilyl cyanide can be prepared from lithium cyanide as shown here, but is also commercially available. Cyanodiethylaluminum can be obtained from triethylaluminum and hydrogen cyanide. Both reagents are less volatile than hydrogen cyanide and can be purified by distillation. Sodium or potassium cyanide are almost completely insoluble in most organic solvents, and the reaction with lipophilic electrophiles is therefore exceedingly slow. DMSO is often well suited for such reactions, but DMSO is a dangerous solvent, in particular in the presence of bases, and can cause many side reactions. Aqueous ethanol or DMF are also common solvents for cyanide alkylations, but as mentioned, Protex solvents decrease the nucleophilic reactivity of cyanide. The alkylation of cyanide is one of the easiest and least expensive carbon-carbon bond forming reactions, and nitriles are valuable starting materials for many other compounds. Hydrogenation yields primary, secondary or tertiary amines. Reduction can also yield aldehydes, and the addition of polar organometallics to nitriles is a practical synthesis of ketones or imines. Twofold addition does usually not occur. The base-induced dimerization of aliphatic nitriles, the so-called Torpe reaction, yields cyanoenamines. These are also obtained when nitriles are treated with sodium in an inert solvent, however by a surprising mechanism. The first step is the formation of an organosodium compound and sodium cyanide, like the formation of Grignard reagents from organic halides. The intermediate organosodium compounds are strongly basic and immediately bring about the Torpe reaction. Simple aliphatic nitriles, such as acetonitrile, are quite unreactive, and most reactions with nucleophiles require high temperature or strong acids or bases. Hydrolysis of nitriles under alkaline conditions yields amides or carboxylic acids, and treatment with alcohols and acids can yield esters, orthoesters, or N-alkylammides in the so-called Ritter reaction. In the Pinner reaction, nitriles are treated with methanol or ethanol and a large amount of anhydrous hydrogen chloride. The resulting iminoethers are strong electrophiles and can be converted into orthoesters or amidines and even react with weak carbon nucleophiles. Then, treatment of nitriles with acids is one of the best syntheses of tetrazoles. Like other nucleophilic substitutions, also the rate of cyanide alkylation strongly depends on the structure of the electrophile. Here are some examples of the relative rate of substitutions in acetonitrile and in the presence of a crown ether. Because of the low solubility of potassium cyanide, these results may depend a lot on the cyanide particle size and on the amount of crown ether. Interestingly, in the case of hexyl and benzyl halides, the chlorides reacted faster than the bromides. Secondary halides underwent both substitution and elimination. Some secondary alkyl chlorides can be converted into nitriles with sodium or potassium cyanide, as shown here and on the previous slide. DMSO is particularly suitable for these reactions. Cyclohexyl chloride, however, mainly yielded cyclohexene. If elimination is a problem, one alternative is the use of sulfonates or sulfates as electrophiles. These are more resistant to beta elimination than alkyl halides. The monofunctionalization of symmetric dielectrophiles is always a challenge. In this example, a low yield of chlorovaleronitril was obtained by treating 1,4-dichlorobutane with half an equivalent of aqueous sodium cyanide and a phase transfer catalyst. With unsymmetric dielectrophiles, however, better results can often be achieved. In this example, the primary bromide was substituted faster than the secondary, and with only a slight excess of sodium cyanide in ethanol, 57% of the mononitrile resulted. Benzylic chlorides are much more reactive than simple aliphatic chlorides, and here a quantitative yield of the mononitrile was obtained in refluxing aqueous ethanol. In this example, the substitution was performed with a large excess of potassium cyanide and 18 crown 6 in dichloromethane. In this solvent, SN2 reactions proceed only slowly, and no displacement at the 4 highly reactive chloroethyl amino groups occurred. Dichloromethane itself is a poor electrophile and reacts with most nucleophiles only slowly. In my video about the Williamson ether synthesis, I discuss the inertness of dichloromethane more thoroughly. In this example, both elimination and substitution occurred simultaneously upon treatment of a diiodide with an excess of sodium cyanide. Neopentyl-type electrophiles are unreactive and will either undergo elimination, as in the previous example, or undergo substitution only slowly. Here, even after heating for 24 hours with a large excess of tetrabutylammonium cyanide in DMF, only a partial substitution occurred. A higher concentration by use of less solvent may also have helped to increase the substitution rate. In this example, similar to the previous one, the concentration of reactants was lower still, what caused the formation of a cyclopropane by intramolecular alkylation. This is another example of clean monosubstitution of a dielectrophile. Again, the secondary mesylate reacted more slowly, and the main product was the mononitrile. Despite the high lipophilicity of the dimesylate, it was still possible to use an ionic alkali cyanide as nucleophile. Cyanide readily adds to electron-deficient alkenes, but it is not easy to predict how fast. In this example, the substitution of bromide proceeded faster than the Michael addition. With a more reactive acrylate, however, only the products of Michael addition resulted. Both reactions were conducted in hot acetonitrile with a phase transfer catalyst, but still proceeded slowly because of the low solubility of potassium cyanide in acetonitrile. The alpha protons of nitriles are acidic, what can cause the formation of unexpected products. Here, for instance, treatment of a dibrominated ester with an excess of cyanide gave a high yield of a substituted beta-cyanoacrylate. None of the other potential products was formed in significant amounts. Because of the high basicity of cyanide, electrophiles containing a phenol substructure sometimes oligomerize by aryl ether formation. In this example, however, a substantial yield of the expected nitrile was obtained. As mentioned, secondary nitriles are best prepared from sulfonates and not from halides to prevent elimination. Here, despite the high lipophilicity of the starting electrophile, treatment with an excess of sodium cyanide in DMF gave the target nitrile as the main product. In this example, though, the substitution did not proceed as expected, and only a low yield of nitrile was obtained. Cyclohexyl and related halides often undergo elimination faster than substitution. Some substituted cyclohexyl electrophiles do, however, undergo mostly substitution. Enol ethers are not formed readily by beta elimination, what may have been one reason for the result obtained here. Then, in this case, the most stable conformer with only one axial substituent does not undergo elimination readily, because being equatorial, the bromine atom would not have any neighboring antiperiplanar hydrogen atoms. I've sketched here the most likely trajectory for the cyanide anion during the substitution as an arrow. Sulfonates are less prone to eliminations, and with mentyl tosylate a clean nucleophilic substitution could be achieved. One alternative to the treatment of electrophiles with alkali cyanides alone are nickel-catalyzed substitutions. These proceed under less basic conditions and sometimes give better results. A large number of additives and a lengthy optimization may be required, though, as in this example. Interestingly, phosphocane bases may also help to prevent elimination. In this example, catalytic quantities of 2 phosphocanes promoted a twofold substitution with cyanide, probably by acting as phase transfer catalysts. Tertiary electrophiles that may eliminate do not usually undergo nucleophilic substitutions. Some few electrophiles, however, such as alpha-haloketones or aldehydes, sometimes yield substitution products upon treatment with nucleophiles, even under alkaline conditions. In this example, a benzylic alpha-chloroaldehyde was converted into an alpha-cyanohydrine by treatment with potassium cyanide and 18-crown-6. A more general method are substitutions with trimethylsilyl cyanide under slightly acidic conditions, as in this example. One potential side reaction is the formation of formamides by Ritter reaction. Other potential byproducts are isonitriles, because cyanations with silyl cyanides often proceed by initial formation of an isonitrile, as shown here. Also, weaker electrophiles than halides or sulfonates can be used to alkylate cyanide. Heating a neat mixture of powdered potassium cyanide and butyrolactone to almost 200 degrees Celsius gave a good yield of substitution product. Lactones are, however, more reactive than simple aliphatic esters, and the latter do not readily react with cyanide. More reactive are benzylic or allylic esters. Allylic esters readily form allyl complexes with palladium 0, and these can react with cyanide to nitriles, as shown here. Allylic alcohols can also be converted directly into nitriles, for instance by treatment with hydrogen cyanide and cuprose chloride. Few examples of such reactions have been reported, though. Some alcohols can also be converted into nitriles directly by treatment with mixtures of sodium cyanide and chlorotrimethylsilane. Even secondary alcohols have been used as starting materials, as shown here. With cyclohexanol, however, mostly a Ritter reaction with the solvent acetonitrile occurred. Even amines that readily form carbocations may alkylate cyanide. This here is an example of the nucleophilic substitution of a dimethylamino group from an aminomethyl pyrrole. Let's have a look at some further potential side reactions. When alkali cyanates are alkylated in DMSO, many byproducts can be formed. In this example, the starting mesylate also underwent hydrolysis, elimination and oxidation to a ketone. In DMSO, mesylates can racemize by substitution with sodium mesylate or undergo hydrolysis with retention or inversion of configuration. Reaction with DMSO can yield alkoxy-dimethylsulfonium chlorides, the intermediates of the Swern and Kornblum oxidations. These may then react further to yield ketones, alkyl chlorides or methylthiomethyl ethers. Hence, cyanide alkylations in DMSO should be conducted with a high concentration of cyanide and as little DMSO and water as possible. Isonitriles are a further potential byproduct of cyanide alkylations, in particular with electrophiles that readily form carbocations, as in this example. But also during bimolecular substitutions, isonitrile formation can become a significant side reaction. In this example, 8% of a secondary isonitrile was obtained, along with an alkene and the expected nitrile. One further potential side reaction is the isomerization of alkenes, especially when allylic electrophiles are treated with the highly basic alkali or tetraalkylammonium cyanides. Here, despite conducting the cyanation at room temperature, extensive alkene isomerization occurred. Sometimes, in particular when the electrophile is sterically crowded, cyanide may attack the halogen instead of carbon and reduce the electrophile. In this example, the main product was that of dehalogenation. As byproduct, either a cyanogen halide or cyanogen can be formed. Another problematic group of electrophiles are those with electron withdrawing groups. The initially formed substitution product is strongly acidic and will be immediately deprotonated by a cyanide. This can cause single or multiple alkylation of this product, as in this example. Cyanoacetic esters are better prepared by esterification of the acid, which can be prepared in high yield from chloroacetic acid and sodium cyanide. Some electrophiles form unexpected products in the presence of strong bases such as cyanide. 4-nitrobenzyl chloride, for instance, gives no benzylic nitrile but only a stilbene when treated with sodium cyanide. This stilbene is simply formed by base-induced dimerization, as sketched here. Here are some more, mostly recent examples, but many more have been reported. You can also find these references in the description of this video. Because nitriles are such important intermediates, I'd like to show you some alternative synthesis. Similar to the amoxidation of alkanes is the amoxidation of alcohols or aldehydes, which often proceeds under milder conditions and may even be suitable for laboratory preparations. A further alternative is the dehydration of amides, but these are not always readily available or as easy to prepare as one may think. Ammonia is a poor nucleophile, and acylations of ammonia often give low yields. There are also some electrophilic cyanide derivatives, for instance cyanogen halides or sulfonyl cyanides, which react with polar organometallics or other carbon nucleophiles to nitriles. Then oximes of aldehydes easily eliminate water. This reaction often proceeds more readily than expected and is irreversible. A further nitrile synthesis is the base-mediated condensation of ketones or aldehydes with sulfonyl isonitriles, such as Tosmic. The yields are often high, but the reagent is expensive and generates a lot of waste. For nitriles that cannot be prepared otherwise, however, this can be a valuable approach. Closely related is the reaction of sulfonyl hydrozones with cyanide, which also yields nitriles. Again, this approach is particularly interesting if the target nitrile cannot be prepared by nucleophilic substitution. The next video of this playlist is about the reaction of cyanide with epoxides. Epoxidation is an inexpensive strategy for the activation of alkenes, and the nucleophilic ring opening by cyanide therefore a relevant method for the preparation of nitriles.